Okay, let's talk about Module 7, transmission. Transmission primarily refers to the transmission lines overhead and underground. And let's look at what our module objectives are. Discuss the key aspects of transmission lines, conductors, shield wires, structures, etc. Explain the key differences between AC and DC transmission lines. Discuss overhead and underground transmission facilities. Applies lessons learned about transmission, primarily interconnections between utilities, to the power system simulator. Okay, so we're going to start out with talking about conductors and transmission lines. Okay, there are different types of conductors used. There's solid, single strand, there's stranded, there's aluminum conductors, steel reinforced, and there are others. But the basic ones are, solid or stranded. In the ACSR type, the steel is in there to give more tensile strength, so you can pull on the conductor harder. So on transmission lines which have long spans, you can lift the sag up, off the ground higher by applying more tensile strength and tension. Used to call high tension lines wires. It's because of the high tension, and the steel helps provide that strength. And you can order these conductors with different numbers of strands of steel versus aluminum versus copper. Okay, in the American Standard Wire Gauge, which we talked about earlier in DC, when we were talking about the DC fundamentals, it basically goes up to the 4/0 size as being the biggest conductor. And then you get into the circular mills concept. A circular mill is equal to the area of a circle with a 0.001 inch or 1 mil diameter. And how many one circular mill circles can you draw across the surface area? And that's basically your circular mills. And normally it's rated in 1,000 circular mills, KCM. So it might be 1,200 KCM, which is 1,200,000 circular mills. So that's how you generally size the larger conductors. Now when you're looking at a transmission tower close up here, you'll see the insulators and vibration dampeners and bundled conductors. So let's look at those a little bit. The insulator, a lot of the older types are the Bell insulators. They're like 6-inch length. I mean, they spread out wider than in a disc, but they connect up about 6 inches, and you put as many as you need to get the insulation level you desire. They come with skirts and what have you. The newer ones are the polymer. They're more of a rubber. They're lighter. They're more shot protection. They hold up well or hold up better with rifle fire and those things. Now the vibration dampeners, those are little weights, and what happens is on a transmission line you have a lot of 60-cycle vibration from the magnetic fields of the changing currents, and what happens is you get a transmission line that's vibrating, and if that ever resonates or syncs up, you end up with this type of a condition. And those wires, they can basically vibrate and take a whole transmission line down. 10 miles of line can collapse through that extreme vibration, and it's happened. So vibration dampeners are actually mounted at a certain little formula distance away from the connection point, and that is supposed to dampen the vibration to avoid resonance. It's kind of like seeing a tire on the freeway. It's the car next to you and it's vibrating like crazy. It goes into vibration because the tire's not well balanced. I think everybody's seen that. Well, this avoids that on a magnetic field changing power system. The bundled conductors say that, let's put on multiple conductors. Hey, we already got the transmission line, we got the right-of-way, we've got, we're investing so much money in all this. Let's just add a second or a third, even a fourth conductor so that we can double, triple, quadruple the amount of power flowing on that line. So that's why you'll see bundled conductors. In this case, you have 2 conductors on 1 phase. Now here's a DC transmission line. Now notice there are only 2 phases or poles. They're called poles on transmission DC lines. So you have the AC three-phase going into a converter station, which converts AC to DC. Then you have plus or minus going poles going down the line to the other side, the other converter station, where you convert DC back to AC. Now, some of the advantages and disadvantages. The advantages of DC is you only actually have two conductors or two poles versus a three-phase where you'd have three conductors. And so the right-of-ways are narrower. You save in one conductor. And the cost for the converter stations, which is kind of a negative, is usually paid for by the savings of the third conductor when a line is typically 200 or 300 miles long. So you have training issues and equipment issues on the converter stations, but on the other hand, the frequency is 0. You can connect 60 cycle systems to 50 cycle systems. You have much better power flow control because you can control the amount of power flow on the DC by the converter station operation. So DC is, it has its advantages. Some DC lines are short, not for economics, but for tying 50 cycle, 60 cycle systems together. There's a few advantages towards using DC. This case, this particular one, is plus or minus 500 kV. So between the two poles, you actually have 1,000,000 volts. You can use earth return ground as in case one line is down. You can have some backup reliability constraints you can, or options that you can have if need be. But DC transmission is something that helps for flow control, economics, and in some cases system stability and reliability. Here we have a conversion, a transition from overhead to underground, okay, in transmission underground. Now what you're looking at there is a transition called a pothead. And up on the very top you have, well, let's start over here with the transformer in the background. Here's a disconnect switch. And then after the disconnect switch, you're coming into the pothead, which actually has an underground transmission cable going into steel conduit. And then over here you have a lightning arrestor to protect it. The lightning arrestor helps clamp voltage so you don't destroy any of the underground cable. So this is the pothead that's going overhead to underground. There are 3 of them. 1, 2, 3. And the lightning arrestors. Okay. Here is underground transmission. Steel conduits, 230 kV transmission, single phase each. And that's basically the vault and the structural support for the underground transmission. Here's an underground splice. Okay, the splices are pressurized to keep moisture out. You don't want to have moisture in underground cables. That would cause problems with the cable. So you'll see that the splicing is very elaborate and pressurized. Here we have a gentleman putting together a splice. And module summary here for transmission is, number 1, we discussed the conductors and shield wires and structures a little bit here. We talked about AC and DC transmission lines. We discussed overhead and underground transmission facilities. And we're going to apply lessons to transmission on the Power System Simulator. I would like to note, I mean, when it comes to transmission, you know, this is kind of an overview. We could get into the different types of structures and get into, you know, how you ground it, but we're still looking at this particular course is really geared not to get to nuts and bolts on how transmission lines are built, whatever, but some of the general concepts of transmission lines. We spend more time on other areas that are more significant for understanding what's going on, but The one thing I would like to add that I see didn't have a slide for is the static wire up on the very top. And you can see it in this picture here. But on the very top is a static wire, sometimes called a ground wire, sometimes an earth wire, sometimes earthing wire. But the idea is a static wire is connected to the structure, which is grounded, so that lightning is attracted to the static wire. So if a lightning strike hits the static wire, that lightning energy will go into the towers, usually 2 or 3, depends on the magnitude of the strike, and dissipate into the earth. Hopefully it keeps the lightning off the conductors so that the conductors are operating with their 3-phase AC without being affected by lightning. So if I were to add anything extra, I'd say, you know, the discussion on shield wires, static wires is probably the most important. We do have more information later on transmission line, how they behave and react, but structurally that's basically how it's set up.